Hello, welcome to a video about temperature scales. So, random bit of background information. Thermometers measure temperature using materials that detect and respond to changes in temperature. So in a simple thermometer like we've got on the left, alcohol, which is dyed red, expands and contracts at a regular measurable rate when it's heated or cooled, and this can be calibrated accordingly for scales. So when you pop your simple thermometer into some hot water, that alcohol is expanding and shooting up the little tube in the middle of the thermometer to whatever temperature. So it's been calibrated for that. With our infrared thermometer, so the thermometer on the right, this infers temperature by measuring the infrared, which is electromagnetic thermal radiation emitted by an object. So for anyone getting like a COVID temperature check when they're walking into an airport or even like a shopping centre or something, the temperature gun is measuring the amount of infrared thermal radiation coming off that person's forehead, for example, and then that will then be converted into a little temperature on the screen. So temperature scales were produced by assigning arbitrary values to reproducible temperatures, and then dividing the interval between those two temperatures into a fixed number of parts called degrees. The reproducible temperatures used were the freezing point and the boiling point of water. So these are easily reproducible, hence why they were used. With Fahrenheit, the arbitrary value assigned to the freezing point of water, so FP, I've done a little key up the top here, so FP is freezing point, BP is boiling point. The arbitrary value assigned to the freezing point of water was 32, and to the boiling point of water was 212. So this interval was divided into 180, which makes sense because there's 180, or the difference between the two is 180. That therefore means that 1 degree Fahrenheit is equal to 1/180th of the difference between water's freezing point and its boiling point. To me, that just seems like a bit random. Like, why would you have those numbers as your freezing and boiling points? But each to their own. That's how Fahrenheit works. With Celsius, originally, so who was the guy? It was Anders Celsius. I think it was Daniel Gabriel Fahrenheit for the inventor or pioneer of Fahrenheit. So originally, Anders Celsius assigned a value of 100 to the freezing point of water and a value of 0 to the boiling point. This value was divided into 100, which makes complete sense, and therefore each degree Celsius, so 1 degree Celsius, is equal to 1/100th of the difference between water's freezing and boiling point. A guy called Carolus Linnaeus later reversed this to 0 as the freezing point value and 100 as the boiling point value, and this is because it was known that water boils due to an increased heat content, so it made sense to flip the values there. I think personally, maybe I'm biased, that Celsius just makes a lot more sense, but you can decide which you prefer for yourself. So to convert between the two, we've got two rules here that we can use. So the top rule is for converting from Celsius to Fahrenheit. What you do is you multiply the temperature in Celsius by 9/5 and then add 32. To convert from Fahrenheit to Celsius, you minus 32 from the Fahrenheit temperature, times by 5 on 9, and that'll give you your temperature in Celsius. These rules, hopefully you can see, are the same rule, but they've just been rearranged to make either the temperature in Fahrenheit or the temperature in Celsius the subject. The value of 5 on 9 is derived from the differences that each degree of Fahrenheit or Celsius represents in each of their scales. So in Fahrenheit, 1 degree is 1/180th. In Celsius, 1 degree is 1/100th. This simplifies down to 9 on 5, hence that's why we've got the 9 and the 5, or the 9 on 5 and the 5 on 9 in this equation. The 32 just adjusts for the difference in freezing point value. So the freezing point of Fahrenheit is 32, freezing point of Celsius is 0, so the difference between the two is 32. So some worked examples. Liquid nitrogen has a boiling point of negative 196 degrees Celsius. What is this in Fahrenheit? So to work this out, we'll write our rule. Temperature in Fahrenheit is equal to temperature in Celsius by 9 on 5 and then plus 32. So that means that the temperature in Fahrenheit is equal to negative 196 by 9 on 5 plus 32. And then if you pop that into a calculator, you'll get an answer of negative 320. It's 320.8. Sig figs is a bit off there, but whatevs. So your temperature in Fahrenheit is negative 320.8 degrees Fahrenheit, so that is equivalent to negative 196 degrees Celsius. Next work example, Daniel Fahrenheit assigned a mixture of ammonium chloride, ice and water, a temperature of 0 degrees Fahrenheit. What is this in Celsius? So just use the other rule, which is the this rule here, rearranged. So temperature in Celsius is equal to temperature in Fahrenheit, and then minus 32, then times by 5 on 9. If we pop our temperature in Fahrenheit into the bracket, so 0 and then minus 32 by 5 on 9, we'll end up with minus 32 times 5 on 9, and that will be equal to negative 17.8 degrees Celsius. So 0 degrees Fahrenheit is equal to negative 17.8 degrees Celsius. So as I touched on before, absolute zero is the absolute minimum temperature possible. It's predicted that at this temperature, particles will be motionless, and this is when the pressure will therefore be equal to 0, because pressure is just essentially the atoms of a gas like hitting the container or the outside edges of, or the inside edges of whatever is being used to contain that gas. Interestingly, NASA and MIT managed to reach a temperature of somehow 1/1000th of a degree above absolute zero, and the atoms ended up behaving quite strangely. I think they kind of became motionless, but they also combined into one super atom, so matter does appear to behave a bit weirdly at this temperature. A French, I'm pretty sure, guy called, I'm not even sure how to pronounce his name, measured a fixed volume of gas at different temperatures and extrapolated to work out what the temperature would be if the pressure was 0. So if the pressure was equivalent to when the particles were motionless, and he was able to determine that the temperature when particles were motionless was about negative 273 or thereabouts degrees. This experiment was repeated with greater precision, and it was determined that this value here, negative 273.15 degrees Celsius, is equivalent to absolute zero, so the lowest that you can go. Just to elaborate on the experiment that this person would have conducted, so these temperatures up here would have all been experimentally determined, and this would have been, so the volume of gas is fixed, these are the different pressures up here, and then the increasing temperature. When the temperature was 0, the pressure would be like the y-intercept, and then using like just a general y equals mx plus c rule, they would be able to work out the x-axis value when pressure is equal to 0. So that's how this value was determined. The Kelvin scale uses absolute 0 as its 0 term, so it starts at absolute 0. And 1 Kelvin is similar to Celsius in that it's 1/100th of the difference between the freezing point and boiling point of water. So converting between Kelvin and Celsius is pretty straightforward. If you're going from Celsius to Kelvin, you just have to add 273.15 degrees. If you're going from Kelvin to Celsius, you just have to minus 273.15 degrees. If you want to convert from Fahrenheit to Kelvin, you first have to convert to Celsius, and then you can convert to Kelvin. So a worked example, the lowest temperature ever recorded on Earth is 184 Kelvin. This was in 1983 in Antarctica. This isn't necessarily the lowest temperature ever that the Earth has ever experienced, but it's just the lowest ever recorded. So to work this out in Celsius, we'll use our rule. Temperature in Celsius is equal to temperature in Kelvin minus 273.15. So this will be 184 minus 273.15. Therefore, the temperature in Celsius is negative 89.15 degrees.